Right. Redox is short for reduction and oxidation. Okay, so we call them redox reactions. Okay? So what you need to know is... You don't need to write that down. What you need to know is that if I look at like all of the possible chemical reactions there ever could be. And then you want to write this down? Yes. Yes, write it down.
Oh, write it down.
Okay. These can be broken into two categories. Okay. Those categories are going to be redox, which we're learning about today, and double replacement. Reaction.
If you're so good on this test, can we watch Louis?
Yes.
No.
What band?
This isn't banned.
What?
Okay. So we have double replacement and redox. Now, we've learned about one type of double replacement. What is it? Thank you. Neutralization.
Oh, really?
It's a type of, yeah, we talked about that. Neutralization, okay? So, if I say on a test question, multiple choice question, if I say, is this reaction a type of redox reaction, and I give you an acid plus a base, is that true or false?
False.
False, right? Because neutralization is a type of double replacement. Double replacement is its own kind of category of reactions. Now, what about redox? Give me some.
It's like the one that goes here. What is it?
Yeah, double replacement. The type of redox, we already know some. Combustion.
Wait, what is redox?
We're getting there.
Oh, okay.
Single replacement. What else? Synthesis. What else? What's the last one? Decomposition. So another kind of altered test question is because it might be online and you might have to have that multiple select where you select all that is true, which many of us struggle on because either we don't read the directions and we don't remember to select all of them, or we just have a hard time. If I say select all that are types of redox, and I give you these 5 things, or 6 things actually, which ones would you select?
All of them, but neutralization and double.
These are all types of redox reactions. Neutralization is not. Any type of double replacement is not. And we'll see why that is in the future here. Okay? So, what is redox? All right? Redox, when we look at redox equations, we want to look at what are the electrons doing as we move through this equation. Right? Redox, and that's what you need to know about why do we do this? We want to look at what is happening to electrons. Okay? What's happening to electrons as we move from the left to the reactants and to the products. All right? So this box here is very important because reduction, you need to know what reduction and oxidation is, because one of the first questions I'm going to ask you is, looking at this equation, which one of these elements is being reduced? Which one of these elements is being oxidized? Well, you need to know what those words mean to be able to answer that question. Reduction is the gaining of electrons. Oxidation is the losing of electrons. Now, here's where you need to really make sure you are focused when answering these questions, because we are dealing with electrons, which are negative things, right? So if I look at reduction, gaining electrons, if you gain negative things in your life, what happens to your attitude?
Negative.
Probably gets more negative. If you gain electrons, what's happening to the element?
It's becoming negative.
More negative. Okay? So reduction is becoming more negative because they are gaining negative things called electrons. Just the opposite, oxidation is losing electrons. So if you lose negative influences in your life, hopefully your attitude becomes more positive. So these are just characteristics of when I ask you what's being oxidized, what's being reduced, these are some things that you're looking for. Is something gaining electrons? Is it becoming more positive? Is it becoming more negative? What's going on?
I don't think I could handle that enough since break my heart.
What?
All my negative things.
Thank you.
Okay.
It's an important thing.
So, because we know we're looking at oxidation numbers, because we're looking at electrons, now we need to relook at oxidation numbers. Because this is where the exceptions are. Not everything up there has a set oxidation number. And you're like, well, of course, you taught us that the B block metals don't. They vary. Well, there's more than just that. Most of your nonmetals have completely weird and varying oxidation numbers. Okay? There are a few rules that we need to follow from now on moving forward when finding oxidation numbers. Okay? Let's go here. Those rules are, and I'm giving the first kind of trumping rules. Like these are the number one and number two rules that trump every other rule. Are you ready? So the first rule is one that you already know. Every single compound.
Are we still on redox?
Yep. Every single compound has an overall charge of what? Every neutral or zero.
These are exceptions.
These are not exceptions yet. You've already been taught that. Okay? It has an overall charge of zero. That's going to be important moving forward here in a second. Okay? And that's not an exception. That's not going anywhere. The number two rule is somewhat of an exception. That number two rule is anything alone. Alone means unbonded. That means it doesn't have a partner. It's by itself.
O2.
Like oxygen, like all of your diatomic. When they are in their diatomic state, they're all alone. Okay? These also have a charge of zero.
Why is that an exception?
It's not really an exception because they're in their ground state when they're by themselves.
Yeah.
In their ground state, they have a zero charge because their protons match their electrons. They're just not happy because their outer shell's not full. Yes?
I'm kind of lost. What are we talking about? This is applying to what?
We'll get there. Okay? This is applying to how we find our new oxidation numbers. Right? So, some examples of this. You ready?
Well, you're saying depressed people are just O2s.
Yeah, no friends. All right? If I say that I want to form water by adding hydrogen and oxygen. Ready? Hydrogen, y'all probably might want to do this example. I don't know why I keep doing that. Would you all agree with that equation?
What?
No.
Yeah.
No.
You have to put water, don't you?
It's not balanced.
Don't you have to put water?
It's not balanced yet, but the skeleton's correct, right? Yes?
Yeah.
And now that we know about redox, we need to find the oxidation state of everything in this equation. So this is where we go to our oxidation rules, right? Do numbers 1 and 2 apply to anything up here?
No.
Yes, compound
The compound,
applies to H2O.
right? So the overall charge of H2O is going to be what?
0.
0. I put that 0 out here for a reason, right? It's not the charge of hydrogen, it's not the charge of oxygen, but when I add those together, it's going to be 0.
Yeah, because aren't those two both zero? They're supposed to be.
Both of these are
It better be.
charges of 0. Why?
They're alone.
They're alone. They follow rule number 2.
They have depression.
Everybody see that?
Yeah.
That's something new today that I'm kind of reteaching how to find oxidation numbers. When they're by themselves, these are unbonded things, they have an overall oxidation number of 0. Yes? Hydrogen and oxygen on water are not 0 because they're bonded, but their overall charge, when you add their charges together, come out to be 0.
0 plus 0 does not equal.
Okay?
That is crazy.
So now you might be thinking, okay, they're by themselves. We know the overall. We kind of get number 1 and number 2. What about? So how do I find hydrogen and oxygen if things have changed? Like, what do I need to know now? So here we go. Here's your next set of rules. These are like tier 1 was 1 and 2. Here's your second tier to where you follow these only after you follow number 1 and number 2, right? So your biggest rules here are
Number 3.
oxygen is always going to be minus 2. Even though there's an exception to that, but we're not going to go through that exception right now. So when you see oxygen, you're going to put negative 2. Hydrogen will almost always be positive 1.
Heck yeah.
That's still.
And notice how I say almost.
Is that number 4 or is that along with 3?
What do you mean?
Like the rule number.
This is 3 altogether.
Okay.
This is like 3 altogether.
Whoa.
Okay?
What is that? Is that a 1?
1 plus 1. Plus 1. Right? Fluorine will always be minus 1.
You're saying that's actually important, right?
And here comes a good one because this is not an exception to what you already know. Groups 1 and 2. So look at group 1 and 2 on your periodic table. Those are your alkali metals and alkaline earth metals. Those are the same. They stay normal. Which means, what does group 1 always have? Positive 1. What does group 2 always have?
Positive 2.
Now, be careful. The exception to that is, look at rule number 2.
Anything alone unbonded.
Right? Besides hydrogen, which is still number 1, but unless they're by themselves. So if I put a group 1 metal by itself, it's 0. Does that make sense? If I put a group 2 metal by itself, it's 0.
Unless you pair it with something.
But if I pair it, now we go by what we've always thought it as.
If oxygen by itself is 0.
0, but when it's bonded,
It's negative 2.
it's negative 2. But the overall compound is going to be 0. So let's go back. Let's go back to this example, right?
Like if it was like, say, potassium and oxygen. Like,
Well, let's do this example right here. What?
So an easier way to say rules 1 and 2 together is any item that's in an equation will equal 0, like because that's compounds and alone. That's the only 2
that's
options.
too general. It's too general to teach it that way.
Okay. 'Cause,
Okay.
I mean, compounds and alone are the only 2 options you have in an equation.
Right. Question, Rebecca?
Wait, so hydrogen by itself is it 0 or is
Yep.
it 1?
0. Only when it's bonded do we do that second tier rules. Okay? So, you all understand why this hydrogen is 0? It's by itself. This oxygen is 0 because it's by itself. But these are not by themselves. So now you need to ask yourself, did Mr. Steinke teach me a rule about hydrogen? Yes, I did. What is it?
plus 1. So shouldn't it be?
Plus 1.
I'm not even going to say anything.
Oxygen, is there a rule?
Mm-hmm.
Yeah, but it's 2.
Minus 2.
Oh. Not to
So now you might be thinking, plus 1 minus 2 does not equal 0.
Indeed, it don't.
Nope, there's 2.
But how many hydrogens do I have?
2.
2 times 1 is 2 minus 2. That math is going to be very, very essential because, one second, did I give you a rule for sulfur? Did I give you a rule for phosphorus or for nitrogen? So from now on, you can't just go to your periodic table and say it's going to be plus 3, minus 3, all that. And really, guys, I've given you rules for almost all of the metals. These are just, we need to do the math to find the charges of your non-metals. Okay? Let me give you an example. You have a question?
Well, I was just gonna say, like, so is every compound like together? Are they all gonna equal 0?
Yep.
Or are they exceptions to that?
There's no exceptions. We can say polyatomic ions, but I give you the charge. And they should equal that charge. And we're going to go over that next class. So I don't want to melt your brains too far today. Okay? So here's an example. Here's a really good quiz and test example. You ready? Sulfuric acid. I give you that compound. And the question is, guys, remember this is all building to what we need to get to in these redox reactions.
This rule 4.
We'll get that. It has all the rules. Well, except for by itself, right? Because nothing's by itself. First off, this is an example. This is an example, right? So the question is, you need to give me the oxidation state of every element in that compound.
Okay.
So how to do that, you should be asking yourself, okay, is it by itself?
No.
Is any of those compounds by themselves?
No.
They're all bonded to something. However, the overall charge of this compound should be
0.
That's why I'm putting that 0 off to the side. Right? Does hydrogen have a rule?
Yes.
It's always.
Plus 1.
If you write just 1, it's going to be wrong because these are oxidation numbers. They have to have charges on them. If you write 1 only, I'm going to count it wrong.
What do I do for like if
So
it
that
doesn't have?
sounds good for H and separating it from SO4.
No, this is sulfuric acid, H2SO4. Okay? Does sulfur have a rule? Does not. Does oxygen have a rule? Minus 2. Yes? So now we have everything but sulfur. This is where you need to do the math that I was talking about. Are you ready? Everything in the compound has to equal 0. So here's the math. I have how many hydrogens?
2.
Each one has a charge of
Plus 1. Sorry, plus 1.
plus 1. Does that make sense? When I add those charges to sulfur, which I don't know, that's a terrible S. How many sulfurs do I have? 1. When I add sulfur then to oxygen, how many oxygens do I have?
4.
What's the charge of oxygen?
2.
All of that has to equal 0. Oops. Now what your job is to do that basic math and find the missing variable to where when you plug in that number, this equation equals 0. Go ahead and do that.
Okay.
Your answer should be the same as everybody around you. Write it down, circle it, look at somebody else's paper or whatever they're doing. Yeah, guys, some of you can do this in your head by all means. The math doesn't get harder than that, at least today. We're finding what's the missing number here to make this equation correct.
I know we have 4 oxygens, but they're both negative 2.
So that would be negative 2 and then negative a.
I'm lost.
6. That's 6.
I was following along so good, now I'm lost.
Right? So, plus 2,
Yeah.
Minus 8. So plus 2 minus 8 is negative 6, right? So what does S have to be to get me to 0?
6. Negative 6.
Positive 6 to cancel out.
Positive 6.
Right.
So what you're saying is, that sulfur has a positive 6 oxidation number in this compound. So what that's saying is sulfur is giving away 6 electrons to make this work. That should if you've been paying attention at all this year, that should sound completely against everything we know about chemistry. But that's what happens. Then that's what the math tells us what happens. Okay? You would never be able to get positive 6 by looking at the periodic table, right? You have to do the math by knowing the rules of these other couple of elements. Does it make sense? Yes? So, if I give you another example, right? Let me give you sodium nitrate. What you need to do is find the oxidation numbers, the oxidation state of each element in that compound. I'm missing one.
We don't know. That should be negative 6.
I don't remember. I just made it up. Sodium has a rule of +1 always, right? It's a group 1 metal.
Yeah.
Oxygen has a rule of -2. Nitrogen does not, so let's do some math. +1, and there is one of them, plus nitrogen, and there's one of them, plus oxygen, which is -2, and there are 3 of them. And it's got to come out to equal 0. So I have -6, and I have 1.
Which would be negative 5.
So 1 plus -6 is -5. So what does N have to be to get me to 0? It's got to be what?
Negative 5. Positive.
-5,
No, positive 5.
positive 5. A positive 5. Good. Yes? So that is positive 5. Because -5 minus 5 is -10. Okay. Why are we doing all of that? What's the importance of all of that? Yes. Oh, I'm sorry. Wrong. Yes, go. Okay. What we need to do is track electrons across these equations. And so there's a little mnemonic device that we can think of when we do this, right? And that's oil rig. Oil rig. You can, yeah. Or back up in these. That's fine. That's fine. These are just how to remember what oxidation and redox means or what's going on, right? And we've already mentioned this. We've already mentioned this. What this stands for is oxidation is what? Losing.
Wait, is that a G?
Reduction is gaining. Now, gaining. Oh, geez. Gaining. What are we gaining and losing? Like electrons, right? This is all about tracking electrons, right? All about tracking electrons. All right, but you need to remember oil rig. So we're going to go to this example. So you all need to write down that Mg plus S gives us magnesium sulfide. That's our first example that we're going to go to.
Or do we have to use the oxidation numbers we just found?
So we'll get to it. Okay. So the question is, is this a redox type of equation? Yes or no? Yes, because it's synthesis, and synthesis falls underneath redox. Because it's redox, you should be able to tell me which one of these elements is being reduced, which one is going to be oxidized. So to start these out, you must first find the oxidation state of each one of these elements on both sides of the equation. So right now, I want you to write oxidation numbers on top all the way across. Go, do that.
So like, would we need to cross these over?
They've already done that.
Oh yeah, because it would cancel. It always cancels out.
I know I'm wrong, but if you're
So
going off of like what we
synthesis
learned
will
from,
always-
ever ago and have been learned.
But we're not. We've changed that.
But that's not in our rules.
It is in our rules.
It's zero. Because there are those.
So, walking around, I see many of you are going to need an eraser.
Nope, look, I did it. Look, I did it.
Why, Rebecca?
Oh, because they're not together, so it has to be zero.
So, magnesium here has a charge of what?
0.
0. Why?
By itself.
By itself. Y'all didn't follow rule number 2. Is it bonded?
No.
So it's 0. What about sulfur? Oops. 0. Why?
It's by itself.
By itself.
He's got depression.
Then we go to magnesium sulfide. Are both of those 0?
It's a compound.
It's a compound. They're together, so now they have charges on them. So magnesium, because it's in group 2, has a +2 charge. And to make this work, sulfur doesn't have a charge or a rule, right?
No.
Sulfur doesn't have a rule. But to make it equal 0, what does sulfur have to be?
-2.
-2. -2. So that's going to be the first step in identifying oxidation, what's being oxidized, what's being reduced. Okay? So I'm going to rewrite this.
Whoa. Where's your face? Can we call him Billy?
Right?
Don't you?
Mg
Okay, he's not rushing. Okay.
plus S yields MgS. Would you all, right? So what you need to do now is you have this, is I want you to connect your magnesiums.
Gotcha. Why would I do that?
Because remember how I said in redox, our goal is to track electrons during the reaction. Yes? So what can you say about the oxidation state in magnesium from left to right?
It gained 2. It's
What's happened to its charges?
It gained its positive.
It lost 2 electrons. It lost 2 electrons to become more positive, right? If you're losing negative things, you become more positive. Yes? What can we say about sulfur?
It gained its oxidation. Because you're gaining more electrons.
It's gaining electrons.
They make this confusing with the gaining and it being the negative.
But it's the confusing part is that electrons are negative. You're gaining and losing negative things. Right?
Yeah.
So now, oil rig, oxidation is losing.
Yes.
Oxidation is losing. So the question is, which one of these is being oxidized?
MgG, magnesium.
Magnesium, because magnesium lost electrons. Reduction is gaining. Rig. Which one's gaining?
Sulfur.
Sulfur.
Yeah. Period.
So those are your answers. Now, moving forward, and guys, that's kind of about where the level classes stop. Okay, that's kind of where they stop. We got to go a little bit further.
Yes.
So, how many electrons is the next question? How many electrons did magnesium lose?
2.
So what I should see there is a 2. It lost 2 electrons because we're going to put all of these numbers into an equation next week to finish off redox.
That's a lot of numbers.
How many electrons did sulfur gain?
2.
So the amount of electrons being transferred and stuff is important just as well. But that's not difficult, right? It's just one more thing you got to think about. That's what would make it more difficult. Okay? So here's your next example. Right? And I'll tell you if I go back. Let's go back. Here's another little side note. Every single redox reaction will only have one oxidation and one reduction element. And you can't have one without the other. So if you're saying to yourself on your quiz or a test, you say, Mr. Steinke, I found what's being reduced, but nothing's being oxidized. That's not true. That can't happen. That's impossible.
It's the other.
Okay? You can't have one without the other. Okay? And only one of them. So if you say, Mr. Steinke, both of these things are being reduced. That's not true either. Only one thing is going to be reduced. Okay? So here's your next example. We're going to say magnesium plus hydrochloric acid yields, and let me rewrite that. That's getting a little big up there. Magnesium yields.
Try to stay even with your writing at least.
Guys,
Yeah, getting better.
What?
I'm so tired.
There you go. So what you need to do with your people around you or whatever you want to do is, the question is, from this equation, I need to know what's oxidized and what's reduced. First off, you need to make sure that it's not a trick question. Is this a redox type of reaction?
Yes.
Because it's not double replacement. So yes, there will be an oxidizer. Yes, there will be a reducer. You need to find it. Go. So for the sake of time, because we're starting to get to the end of class, and I want to make sure like you got at least on the right track, maybe you didn't get all the way to the end. What I should have seen is oxidation numbers on all of these. Hydrogen does have a rule, chlorine does not, but hydrogen's +1, so chlorine has to be -1. Over here, hydrogen's by itself. 0. Magnesium, because it's bonded, plus 2. Chlorine minus 2. There are 2 chlorines. So 2 times negative 1 is negative 2. Plus 2 minus 2 is 0. So there's your oxidation states for everything. Then what I should have seen is that magnesium is different and hydrogens are different on both sides. Which one stayed the same? Chlorine. So chlorine isn't really a part of what we're doing right now. It didn't transfer or receive any electrons. So if you look at magnesium, magnesium goes from 0 to plus 2. What has it done?
It lost.
Magnesium lost electrons, which means hydrogen had to gain electrons. Yes? Because it's gaining electrons, magnesium is oxidized. That means hydrogen is being reduced. Now, will magnesium always be oxidized? You got to figure it out each time. Okay?
Yes, sir.